Good morning, everyone. I am going to introduce our speaker for this morning, but first I'll say a short bit about myself. I am Claire Marvany. I'm a staff scientist in the Quantum Computing and Sensing Group here at Oak Ridge National Laboratory, and I'm a part of the Quantum Science Center where I do quantum optics. So you'll hear from me next week. Today I'm introducing Carleton Coffrin. He's a staff scientist at Los Alamos National Laboratory in the Advanced Network Science Initiative. His research focuses on how optimization algorithms can be applied to applications on infrastructure networks. And he's going to talk about analog quantum computing for you all today. Thank you.
Okay, thank you very much. Can everybody hear me? Awesome. First, I want to say, please ask me questions in real time. I've heard you're a very interactive audience. I love that. Let's get your questions answered. Yeah, thank you very much for the introduction. I'm going to focus mostly on quantum stuff now and less optimization, which is my background. I should mention that I'm a computer scientist by training. I came to quantum computing since I joined Los Alamos National Lab, but I think it's one of the most fascinating and fun topics in the world right now. So you're making the right choice coming to this summer school, and I hope you'll find this to be a really interesting topic. So let's just begin with some motivation. I think you all know that the quantum computers have arrived. You know, I heard yesterday Vivian gave you a great talk about all the different types of qubits. Here's an infographic from Domain of Science, which is a great science communication guy, which shows you different companies that are involved in those different types of quantum computers. And every bubble on this is a quantum computer technology that was announced back in 2022. I'm sure the list is even longer now, but you can see that there's like tons of computing companies doing tons of different things with different qubits. It's a really exciting time. Now, back in 2019, following the development of this hardware, we got quantum supremacy. I presume all of you heard this news. It was in the New York Times when Google announced they had done a computation that could not be done with a classical computer, even with 100 years or 1,000 years on a flagship HPC system. But that was 5 years ago. And where is the quantum computing utopia that we were all promised, right? You often hear that these quantum computers are going to revolutionize tons of different applications, optimization, logistics, supply chain, financial modeling. AI and ML will be done better because you can have quantum machine learning models, molecular simulation, drug discovery, material design, renewable energy, and then of course, quantum simulations for kind of fundamental physics questions. I mean, if all of this was so easy, you would hope we would have had it already. It's been 5 years since we had this supremacy demonstration, right? So the question I want to pose to you as a motivation for my talk is, where is the quantum utility? Sometimes people call this practical quantum advantage, but this is like if we have the quantum computers, why aren't we seeing this amazing revolution in computing that many people talk about? It turns out that this is a pretty tricky question. What will we actually use quantum computers for? That big list I gave you before is kind of, when you start to ask people, okay, exactly how will you use a quantum computer to support like a logistics or a supply chain application, it starts to get very tricky really quick. And everyone is focused so much on doing this quantum advantage demonstration or quantum supremacy demonstration that they don't really think, okay, what comes after that? So I'll just pose it to you, after all the quantum advantage demos are done, then what? Does anyone have a good idea? What's your favorite thing? What's the first thing you're going to use a big, awesome quantum computer for? What was that? Someone proposed RSA. That's a good idea. You need a really big quantum computer for that. Do you know how big? So the question is, maybe we could use quantum computers for breaking RSA. There's a very nice paper by, I can't, Gidney et al., where they project that to break 2048, you need 20 million physical qubits. Seems like a long way off. I think there was a question back here. Your favorite app? Room temperature superconductor, that is a great application. Bonus to you. We have one over here. Shipping optimization. Great proposal, but the details are tricky. Towards the end of the talk, maybe we'll have a chance to get into why that is, because I will cover optimization. Okay, so we've got tons of great ideas in the audience. You guys are awesome. It turns out, to answer this question and really say, this is exactly the workload that we're going to run, and it's going to be big and important and impactful, is a super tough question. It's such a hard question that DARPA, which does the hardest questions in the world, right, made a program called quantum benchmarking just to try to answer the question. If we had the biggest, most powerful quantum computer anyone could dream of, what would we really use it for? And this is a super interesting question. It's very difficult to get into the details. Very recently at LANL, we released this report, which details 6 applications. High temperature superconductivity is one of them. And exactly what you would use the quantum computer for to make progress on those big challenges. But it's complicated. It's like 150 pages for 6 application topics. So go check that out if you want to see some interesting answers to that question. But I do want to also raise this point, which is kind of a cautionary tale for those who might seek quantum utility. Some of you might have caught wind of this big announcement from last summer, where basically an IBM-led paper said there was evidence for utility of quantum computing before getting a fault-tolerant quantum computer. It was such a big paper, it got the cover of Nature. And if you read the subtitle here, it's the Nature subtitle says, error mitigation empowers quantum processors to probe physics that classical methods can't reach. And I think based on the paper, that is a fine claim to make. However, in 14 days after this paper became public, there was an archive paper, Efficient Tensor Network Simulation of IBM's Eagle Kick-Dicing Experiment, which showed that at least some subset of these computations can be done in 10 seconds on a laptop computer. So you got to be really careful if you're going to make these claims of utility and usefulness, for like that we really need a quantum computer to do something. So here's a billion-dollar question. When will we really achieve quantum utility? So that is, impacting real-world problems, not just doing quantum advantage demonstrations. And I call it a billion-dollar question. That is not hyperbole, because Australia has put a $1 billion Australian dollar bet on PsiQuantum, because PsiQuantum is working to build a fault-tolerant quantum computer, and the people in Australia, however that decision got made, had decided it was worth making this big bet that when you build that fault-tolerant quantum computer, you're going to be able to do some really amazing things, and it's going to be super valuable to the world and society. Now, if you look at public vendor roadmaps, they suggest these fault-tolerant quantum computers could come as early as 2026, but maybe as late as 2030. So pretty soon. But maybe we would say, based on this information, quantum utility would come in 5 to 10 years from now. I think there's plenty of people who would say that's a really crazy soon thing, and they think it's going to be more like 20 or 30 years. But that's kind of, if you believe fault-tolerant quantum computing could be useful for something, this is a reasonable target. So why should you pay attention to this course and ask me a lot of good questions? I will try to convince you that quantum utility is already here and nobody knows it. Sounds crazy, right? What is the key insight here? It's about these analog quantum computers. I think they're already amazing and they can do really cool stuff that is valuable, but nobody knows they exist. So like, what's going on? So let's go into just briefly the most important results in quantum computing that no one has ever heard. I don't know what the most important results in quantum computing have been, but I do strongly believe you have not heard of these 4 I'm going to tell you about. First one, in 2018, this is the first paper I know where a quantum computer reproduced the phases of a quantum magnet. So the first simulation done on a real physical quantum computer that reproduced phases of, in this case, it was a 3D Ising model spin glass. 3 years later, the first time that quantum spin liquid phase was observed and verified in any physical system. any material or any physical system. This was done on an atomic quantum simulator in 2021. 2022, this is a result from the team that I manage at Los Alamos, was the first wall clock runtime advantage for a quantum algorithm applied to a classical optimization task. So like what you see usually about quantum optimization these days is like a scaling advantage, which means at some time in the future when the computer is big enough or fast enough, there will be an advantage. This is a real wall clock advantage today. That was in 2022. And then in 2024, we have the first quantum supremacy demonstration with potential clear applications, not just a contrived problem that doesn't necessarily have clear use cases. I will caveat that this result is very recent. It's from March this year. I haven't seen independent validation of it. It still might be subject to the kind of disruption I mentioned before, but it stood a couple months without critique yet. So that seems pretty promising. This paper, you can see the key figure on the right. It suggests that right now on an analog quantum computer, you can do a computation that would take 1 million years on the largest classical computers we have today. Seems crazy, right? Oh, we got a question. Okay, so the question is, this shows that it can do something a classical computer not. Why is it useful? Or why is it more useful than a previous demonstration, right? Well, so this is a quantum dynamic simulation. I believe that has clear applications. And you say, why is it worth investing tons of money in that? Well, we could use these arguments. It's not an easy question. That's why DARPA has a program. But there are people at LANL who study quantum magnets that this could be a really useful support for their research. There are people who study high temperature superconductivity. This is maybe not a perfect model for that, but it's a step in that direction. There's a question down here. Still possible if somebody becomes faster on a classical computer? Yeah, so the question is it still possible someone could find a clever classical algorithm for this problem? So the answer is yes. We don't have any, there's no like proof that says you can't build a great classical approximation, right? In the world I come from, optimization research, the way that we figure this out, there's no proofs that say like it can never be done, but the whole community just studies problems for decades, right? And then you kind of see, oh, well, there hasn't been significant progress on this for many decades in the classical algorithms. So like when there's a big jump and you're like, aha, there was a breakthrough, I knew a good idea. So essentially what this paper is trying to say is tensor network methods, PEPs, like matrix product states, like the best classical algorithms we know, which are the 4 rows on the bottom there, aren't able to touch the type of computation that this computer is doing. Now, someone might come up with a much more clever idea that isn't one of those categories. We can't rule out that possibility. It's just that we know it hasn't happened for 3 months, and that's better than most. And maybe in 2 years, we'll be like, okay, yeah, we're really confident now this won't happen because like people have been trying for 2 years and they haven't succeeded. There's one question over here. The question is, how confident are we for PEPs? I mean, what do you mean by confident?
Very curious on how come people have put their money on PEPs. MPS and DMR, yes, I understand, but specifically for PEPs, I'm a bit confused.
Okay, so essentially the question is like, why do people like PEPs so much and not these other methods? I don't have a stake in this game. So like, if you say people love PEPs, I'll believe you. But what I see is that there's people trying lots of different algorithms. Maybe the communities are not proportionally sized, and some work well sometimes, some don't work well other times. This paper is a good example of how you might build an experiment to convince yourself that PEPS is working correctly at small scales, but is failing at larger scales. Or, well, this is a quantum runtime advantage paper, but it has in it all those elements of like, how do I make sure that this MPS code is hitting the right accuracy and is giving the right answer? But then we enter a regime where we just can't run it anymore. And they do that for all 3 or 4 of the methods that are down below. Okay. So what will we learn today? And I may not have time to cover all of these things, but your questions are the highest importance to me. So ask your questions and we'll get as far as we get. So the first thing I'll try to do is tell you, what are these analog quantum computers? What can you compute with them? What a reasonable computational question to ask. Then we'll go into how do you build an analog quantum computer algorithm? And a trigger warning, I'm going to talk about quantum annealing. It's really cool. You might have heard otherwise. Trust me, it's really cool. Then I will, if we have time, get into some of the challenges and successes of this annealing hardware that we've seen over the years. And very briefly, I have a few slides at the end about the future of analog quantum computing. Okay, so what are these analog quantum computers all about? I like to think of quantum computing as kind of like a stack, like a computer architecture idea, where at the base level, you have like a bare metal physics experiment, which is an analog quantum computer. Typically, what a vendor does is then they take their analog quantum device and then they build one abstraction layer on top of it, which is the gate set, right? The quantum gates. Then that's what a NISQ computer is. If you want to do a fault-tolerant quantum computer, you actually get 2 layers of abstraction. So first, you take a bunch of physical qubits, you gang them together into a quantum error correction code, and then that turns into a gate set, which you can program. So essentially, with each one of these layers, you get like the system gets maybe a little bit slower, but then you get a different model of computation that you prefer because you can suppress errors or you have good algorithms for it. So we're going to talk about the lowest level, this analog quantum computing level. So if you've heard about the gate model before, you can just forget that. That's not relevant to this analog quantum computing model. What we're going to do is program a dynamical system directly and then try to get it to do something useful. You can kind of think of an analog quantum computer as the type of experiment we would do in a laboratory, a physics lab, but it's just highly automated. It's programmable. So now instead of like the setup of the physical system and like how you evolve it over time and how you read it, instead of having like a semi-autonomous with a human in the loop system, now we have a fully autonomous system that can just do it all for you really fast. And essentially what we're going to do is we're going to time evolve the Schrodinger equation based on the system's parameters, but we get to program the Hamiltonian, the amount of time evolution, and sometimes this initial state psi. Now, if an analog quantum computer could do that in the most general model, like we would be done. We wouldn't need like other types of computers, but there's a lot of details that make it difficult to use these computers for things. So the details of what you can do in each one of those blue highlighted sections is actually quite important. So in many ways, if your application is solving the Schrodinger equation, an analog quantum computer is an amazing tool for what you want to do. But what we found is the big challenge is like, does the hardware have sufficient programmability or flexibility to support the application, your favorite application? It tends to be a very tricky question. And indeed, finding a good match of the hardware and applications has been the primary challenge for realizing impact of these computers. Right now, I would say there's 3 major vendors which can sell you this type of quantum device. So we've got D-Wave, QIS, and Pascal. Currently, they range from between 100 and 5,000 qubits. They have coherence times in the order of 5 to 50 time units, and that's normalized to like kind of algorithmic time units. And they implement this transverse field Ising model Hamiltonian. They support reading on one basis, which is, we can call it the computational basis or the Z basis, but that's what the technology is. I'm going to walk you through I'm going to go into this in more detail to explain like what is each of these components, but these are the three big vendors. I think there's a question here and then one over there. Yeah. Yeah, so the question is, you've got some kind of native device, which the native Hamiltonian device can simulate, and you need to map an algorithm and an application to that algorithm to do something useful for you. And it's tricky. Yeah. The question is there introductory material that explains how you can map certain classes of algorithms to certain Hamiltonians? At the broadest scale, you can prove that analog quantum computing is equivalent, like QMA complete to circuit computing. So like from a complexity theory standpoint, they are equivalent. Now, that's maybe very misleading because all of the challenges with like how noise enters the Hamiltonian, like what terms you support, even a polynomial overhead may cause you like just to be totally impractical. So even though like theory says, oh, these are equivalent, I think in practice this isn't true. You really need to co-design is often the term that's used. Pick an application that's like a very good match and an algorithm that's a very good match to what the hardware can do. There was a question over here for a while. The question is, this feels like a physics experiment and not a computation. I think that's a fuzzy line, right? Like what's the difference? And digital computer is just electricity, and resistance. And then we build all these abstraction layers on top of it. And then we have, a Turing machine, right? I don't see any reason not to, let's say, have a whole different model of computation and then do it. So maybe towards the second half of my talk, when we talk about algorithms and stuff, you'll see that maybe there's like something interesting computational, more of a computational angle here. One more and then I'll keep going.
For what Hamiltonian we can do analog quantum computing for that?
So the question is, what Hamiltonians can you do this analog quantum computing for? That's a great question. An experimental physicist would be able to tell you much better than me. I think it's no coincidence that all three of these vendors implement something like the transversizing Hamiltonian, because it's kind of the simplest thing, right? Engineering more complicated Hamiltonians is difficult, but people tell me that they could build the fermionic Hamiltonians in an analog quantum simulator. It's just, they haven't, like it's the way to build it is understood. It's just no one has built one that we can play with yet. So I think that is a great open question. Like, how big is the design space for analog quantum computers? You'd have to ask an experimentalist. I don't really know that question. Okay, so in this model, right, if you have the transverse field Ising model, you get to program these terms of the Hamiltonian, and there's a bunch of hardware-specific requirements. So I'm going to get into that next. So first, let's talk about the Ising model and what that means for the transverse field Ising model. So the Ising model is a classical physical system that is kind of a foundational tool of statistical mechanics, and it can be used to model all sorts of different types of condensed matter systems. So you have a graph, for example, where each site is a particle, and then the edge is describing the interaction between two particles. We'll have a local field that can bias a particle up or down. There are going to be spins. The J term models like the interaction of neighboring spins. And you can see the Hamiltonian for the classical Ising model right there. The quantum generalization of this model, the transverse field Ising model, is that we put the classical Ising model on the Z basis, but then we apply a transverse field on the X basis. So it's a gamma term with the transverse field. And that can do some pretty interesting things. It's kind of the simplest quantum generalization that might be interesting. And I said this already, but like the analog quantum computing hardware restricts what you can do with these Ising models. So in full generality, it would be super interesting, like immediately, but then the hardware restrictions can make it tricky. So let's talk a little bit about the device that D-Wave built and sells. So they have superconducting architecture. So there's these little nanowires that are embedded in a chip, a 2D fab process. And each nanowire is a qubit. You can see them circled in red there. And they have various control signals that go into this device, which allow you to implement this particular Hamiltonian. So basically what is fixed is this X term and the Z term. And then there's a time varying multiplier A on the X and B on the Z. And then you also get to program the local field and the coupling term J from the Ising model, right? And that's the basic part of the Hamiltonian. Now there's more constraints this hardware puts on you, right? So the first big constraint is the time varying functions A and B follow a very specific schedule. They ramp up and down like I show in this picture. And this implements the quantum annealing algorithm. So this isn't just like a generic analog quantum computer. This is a analog quantum computer which only does quantum annealing, which is one specific algorithm. And so you have limited control of what you can do here. Then, because of its 2D embedded, the way the different qubits can interact with each other is restricted to a specific graph that is set up by the hardware. There's a picture of it in small detail. But the good news is they've been able to scale this architecture to really big sizes. So, so the full system is 5,500 qubits approximately. There's a small picture of the graph. It's way too complicated to really understand in picture form. But you could, it's the pattern which I showed you on the right, like repeated many times. And the current systems have about 40,000 2-qubit interactions. There's other things that constrain you that like the linear term on Z needs to be within a certain range. The two-body term needs to be within a certain range. All these details matter once you start to look at real applications. One nice thing about this technology that maybe is underappreciated is it's like insanely fast. So you can get 10,000 executions of this algorithm in about 2 wall clock seconds. So that's actually, for a quantum computer, even a quantum computer, that's actually really impressive runtime. So that's the D-Wave model. Let's talk about QIS hardware design. And I think Pasquale's is similar, but I haven't used their platform, so I don't know for sure. So here we have a similar Hamiltonian. However, it has, say, additional terms. So there's essentially 2 time-varying control parameters, detuning and oscillation, so like omega and delta. And one controls this strength of this Rydberg blockade, and the other one controls the local field that's applied to all of the qubits. And then we have a third term, the 2-qubit interaction term is mediated by this Vij, which is a distance-based term. Currently, you can use these systems with, say, 256 qubits, but they can get much bigger than that. Like, there's no reason this technology shouldn't scale as it progresses. But we do get some interesting restrictions of the hardware. So in this version of the hardware, essentially what you're going to do is you get to program where the atoms live in a 2D plane. So you place them in a grid. There is an example of like a hexagonal layout or a grid layout. And then this Vji term in the Hamiltonian is determined by the distance between 2 atoms raised to the 6th power. And then there's like there's a constant in there as well. So essentially, like as the atoms get closer together, they get very tightly interacting. But you can place them farther apart to make them weaker or no interaction at all. You can imagine power 6 is like very sensitive. Then when it comes to these time varying parameters, gamma and delta, you get a lot of freedom on what you do with this in the platform. So like the picture on the top is a schedule that would implement the quantum annealing algorithm, but you can do much more exotic things like the one on the bottom, which does quantum annealing followed by a very fast quench, which can then change the type of information you're collecting out of the computer. The last interesting thing is the readout is actually taking pictures of the atoms. So here's a picture of some of the atoms fluorescing with a certain state. And so if they fluoresce, you say it's a 1, and if they don't, you say it's a 0. So then you can actually see what's happening when you read the state of the computer. Now, at this point, I'll say, can anyone in the room spot one major limitation of this particular Hamiltonian OR design? Yeah. So you say the distance-based interaction. What about the distance-based interaction? Yeah. So the remark is like, I'll rephrase what you're saying. The 2D embedding of the system may make the distance requirement quite restrictive in what you can implement. Now, what if you could do 3D? Then it starts to become pretty interesting, and Pasquale has said their technology could go to 3D at someday. You're close to what I had in mind. Does anyone have another idea? Yeah. So you say that they can't dynamically control the entangling gate or the two-body interaction. So in this architecture, that's true. You have to fix it ahead of time. However, in like the Lukin group's proposals for future designs, they've actually talked about moving the atoms and then applying gates and moving them and applying gates and stuff like that. So I think the technology could support different like real-time varying bit if they wanted, but the computation will be so bizarre. Like, I don't even think people have proposed what a cool demonstration would be do with that technology. Okay, I'm gonna give it to you. So look closely at this term, VJI equals C over PJ PK. C is gonna be a positive number, and a distance metric is also gonna be a positive number. So the coefficient in front of the two-body term is always going to be positive, which is equivalent to an anti-ferromagnetic interaction in the Ising model. So basically, you can make a frustrated system that is, having weird degenerate states, but at least right now, it's not super clear. How would you implement a spin glass where you have some interactions pulling themselves together and some pushing them apart? That's actually quite a tricky thing to encode in the system. I'm sure there's a clever encoding out there, but it's like, you need to think, if you want to model a spin glass, how are you going to put it into this computer? Let's see, what's next? So the next one is, how can we compute with analog quantum computers? We had that question earlier. Now I'm going to go away from specific hardware details and talk more about math. Any other question about the hardware platforms before I move on to this topic? Okay. So here I'm going to talk a bit about like the types of computations you can do, because it's not super obvious. Well, maybe this one is super obvious. So we talked about before, we're basically building a physics experiment, and we're going to time evolve the Schrodinger equation. So many people agree quantum simulation, let's say unitary dynamics, is one of the killer apps for quantum computers. Even Scott Erickson agrees with this. So we can all get on board. Here are some great demonstrations about how an analog quantum computer within a sufficiently restricted regime is giving you essentially closed system dynamics, and can potentially help with this very obvious thing to do. Now, people have proposed that the quantum annealing algorithm in an analog quantum computer might be good for optimization. That was one of the suggested applications at the beginning of the talk. So this is doing classical optimization. In theory, this technology should be very good for that. In practice, it has been very difficult to achieve this optimization demonstration because of noise and other like thermalization, open quantum system effects that make it difficult to find really high quality solutions. I mentioned before, in 2022, we started to seeing maybe the inklings that it could be useful for this use case. But I want to tell you about two unexpected things that you can potentially compute with these computers, which if you've got a good application in mind, might be exactly what you need to do. So the first one is doing Gibbs sampling of the transverse field Ising model. So if you want to sample the states of one of these systems, but at a finite temperature, not zero temperature. Zero temperature is ground states, right? Like finite temperature is excited states. It turns out these computers, like the noise and the thermalization that the computer naturally does, make it really good and fast for doing this type of a computation. Was there a question there? Yeah? Uh-huh. Sure. So the question is, what are we going to read at the end? And then why is that useful? Let's do the easy case, which is optimization. Okay. So we're going to run the quantum computer, and then we're going to read on the computational basis. And we're going to get a bit vector, 0, 1, 0, 0, right? These computers let you read like the whole bit vector after you collapse the wave function, like per execution. And so here, that vector is some solution to your optimization problem, and it has some solution quality. So then you might run it a few times and pick the solution which is your favorite. In the quantum dynamics example, you're looking at spins being like up or down, right? And you might be curious, does the quantum dynamics of this particular system have an order, or is it a disordered system? So you would run it a bunch of times and like, look, are the spin configurations like kind of aligned together? Are they forming a pattern? Are they just totally chaotic? Those are the types of questions you would ask. You look like you don't believe me. Sure. Yeah. I mean, if you can see all the states, you can compute a correlation function. Like if you, two-site correlation is trivial, right? You just measure like 10,000 times and then you just compute it. Yep. No, you can't do 1 qubit unitaries. You have to, the way this looks is like a line of qubits, one ginormous unitary, and then read. Because you want to read a different basis? So you make a good point. So the question is like, what basis can you read? Can you apply a polystring to check a different basis? The answer is usually no, because you can only do it for sigma z, right? So you make a good point. Like, what can you do when you can only read on one basis? I would say I can't give you like, I would have to give you a whole nother tutorial on applications to fully answer that question, but there's actually quite a lot. And if you look at some of the papers we've written, we actually figure out like, how can you probe what is the fidelity of the state just with one basis measurement? Turns out if you sweep enough parameters, you can do some pretty interesting things. But maybe going back to, I'll go back to this paper right here. No, wait, oh no, it was in this, let me go back to here. So in this paper, so they've got their quantum annealing protocol, and then they have this quantum annealing with a quench. What is this quench about? It is a very clever idea for doing a basis change so you can read an X. So you can't do poly X on all of it, but you can kind of rotate the entire frame of the whole system into X. And then you can read all of them on X. So if you want to, this was the way they certified entanglement of the states in this paper. So I would check out that paper. It's pretty interesting. Yep. Mm. So the question is, what about errors and error correction? In general, quantum computers or analog quantum computers, there's not an error correction theory. So no error correction. There's absolutely error, right? Oh, so you just said as we scale it up, error is going to compound. I don't. That's not obvious that that's true, because you can have error that's only locally applied and has a limited distance. Yes, so there will be a time limit. Just like in any non-error corrected computer, there's going to be like a limited amount of time this thing can run for. And then the question is, does your application fit into that limited time or not? Here's an example where they show they essentially have closed system dynamics up to, let's say, 50 nanoseconds of time, wall clock time, and then things start to become an open quantum system. So below that, you can do your closed system dynamics. But above it, it's just like, sorry, this computer can't do that. You need a better computer. But this is a good segue into my next question, which is like these unexpected use cases. So if your application goal is to sample from a thermalizing distribution, this computer is actually great for it, because the error which you get that takes you out of the perfect quantum computation or closed system dynamics actually allows you to access these excited states. And there are applications where you want to actually see like a spectrum of states at finite temperature. The hardware can actually do this for you quite effectively. That's for sampling from the transverse field Ising model. You can even do sampling from a classical Ising model. In theory, this should not happen, but we have some interesting results that suggest it is possible to do. We don't have a theory for why, but we have a protocol which basically lets you sample from the classical Ising model with these devices, which is pretty interesting. So that's what you can potentially compute without applications. Next up, we have quantum annealing. Questions about the types of computations you can do with one of these computers. Yeah. Uh-huh. So the question is, for any application which you can put into a QUBO, this type of machine can do it. And I would say theoretically, that is true. The details matter. And like what you end up finding is that for an arbitrary application to encode it into a QUBO, maybe you have a quadratic or a cubic overhead. Now you need a quantum computer with 10 million variables. That starts to sound like a problem, right? You say these are Ising models, right? The QUBO is a 0, 1. There's a mapping between the two. So on the first glance, that's an easy translation to make. However, all these computers have noise and errors in how the information is implemented with physical controls. And when you make that transformation, the noise may be amplified or it may be suppressed. So what we find is that if you just take a random QUBO off the shelf and you try to put it into one of these computers, you get terrible results. You really need a Ising model or a QUBO or a lattice structure that's kind of a good match for the hardware's implementation so that you don't have these big overheads. Did you have a question? Mm-hmm. Yeah. So the question is like for physics applications with more complicated Hamiltonians, how like can you map it into these architectures? I would say again, it's the same sort of optimization. Like there is an encoding, so that the short answer is like yes in theory. In practice, I would strongly discourage you from doing it. There's an emerging topic called Hamiltonian embedding, which is like the algorithms for taking one Hamiltonian and turning it into another one, and then like running it on these devices. But usually the overheads are horrible. And then the noise enters the application in a weird way that destroys all the useful information. I would be more inclined to go to a hardware engineer and say, here's my favorite Hamiltonian, Heisenberg 2D lattice or hexagonal lattice. Can you build me an analog quantum computer that matches my Hamiltonian? And if they say yes, that's pretty exciting. Okay, one more?
Yeah, maybe this one because I think for this method, they have one drawback, which is if you want to simulate a say infernal system, you need 2 to the n side of the analog computer to use this Hamiltonian embedding method.
Yeah, so I'm not familiar with the Hamiltonian embedding method you just mentioned, but you say that it requires for fermionic to go to Ising, it's to the n in number of qubits. I can totally believe that would be the case. So there may be cases where it just really is untenable to do that. But if I can give you one message in this talk, it's like, if you're going to use an analog computer, start with the system's Hamiltonian, try to find an application that's a close match. It doesn't need to be perfect, but close. If you start with your favorite application and try to put it in, probably you're not going to get results that you're excited about. Okay, let's do some math on quantum annealing. And I'll try to convince you this is a cool and interesting algorithm. So what's the application motivation here? We're interested in finding low energy or high quality configurations of a classical Ising model. You've seen it there. This has applications in condensed matter theory, statistical mechanics, combinatorial optimization on networks. So we want to solve a classical problem, but we want to design a quantum mechanical algorithm that makes this classical minimization, that somehow helps us doing this classical minimization. So the application is not quantum mechanical, but we hope the quantum algorithm is like a good insight. Now, the best idea out there to do this is this algorithm called quantum annealing. I actually think the name quantum annealing is terrible. It was inspired by, I think, simulated annealing, which is emulating. So that's an algorithm that emulates the cooling of a metal to find high quality optimization solutions. In this one, there's no cooling, there's no thermal dynamics. It's more like a quantum interpolation algorithm or a quantum homotopy algorithm. Like those would have been better names in my mind, but we have this name, so we call it quantum annealing. And the highest level picture I'll give you here is that you start with a well, like a single well potential with a quantum superposition of states. So that's like on the leftmost picture. And all of the state vector is in the ground state of that single well. And then over time, we change that well from a single well to like a very complicated, this is a double well example, but in general, it'd have like a gazillion wells, where the superposition of the state kind of lives in all the wells simultaneously. And if you do the algorithm slow enough, the probability will concentrate in the ground state or the lowest energy state. So that's like the high level picture of how it works. But let's get into the math of it. So what is really happening? This is a carefully designed solution to the time-varying Schrodinger equation that can discover these optimal solutions to the classical optimization problem. So there's the unitary dynamics that we want to model. And all of the interesting stuff is like what happens in this Hamiltonian. It's going to be a transverse field Ising model. That's why people built such hardware to do it. We're going to put our problem of interest on the Z basis. And then we're going to use the time-varying functions and the X basis as kind of our procedure to drive the state towards low energy states of the classical Ising model. At the end of the computation, the probability mass of the state will be on the optimal solution. So when we read psi, it'll collapse to the bit vector that we want to know. To understand this, there's kind of three big ideas. The first one is encoding. So we're going to take a minimization of a combinatorial optimization problem, and we're going to turn it into finding the minimum vector of a matrix. The second one is how we solve that. We're going to use that dynamical system, the Schrodinger equation, as an algorithm to find the minimum vector of a given large matrix. And then the third point is that the physics of qubits makes this algorithm possible. Like if you didn't have qubits, this would be crazy. But because space is cheap in a quantum computer, this actually makes a lot of sense to do. So just to give you a reference, to emulate the quantum annealing algorithm, it's pretty hard to get above, say, 16 spin problem or 16 qubit problem. But with like current hardware, you can do hundreds or even thousands of qubits in this model. So that's pretty interesting. So I'm going to focus on these two and try to take you through all the details. So first, some simplifications and preliminaries. Everything I'm showing you will be real valued, but in reality, it's a complex number, right? We're doing quantum computing. There are some requirements that are not discussed, like I'm not going to talk about the unitariness of all these matrices. Just by coincidence, they'll all be unitary. But all the things I'm showing you just generalize to those properties. It's just that I won't make it super explicit. You're going to see this mathematical term. It's probably familiar to you, but computer scientists definitely don't encounter this. We're going to use the Kronecker product, which is kind of this recursive matrix operator, which is defined right here. You just like put a copy of the matrix in every cell and then expand it. This is how you build exponentially large matrices on a piece of paper. And then, of course, the power of quantum computing is that we get to do our computations over these exponentially large vectors, right? So the size of your quantum state is going to be 2 to the n times the number of qubits, which I show here. Like 1 qubit just has 2 states, 2 qubits has 4, 3 qubits has 8. This is the really cool thing about quantum computing. And in the case of superposition, we would, if we have, say, an optimization problem with 2 optimal solutions, we're looking for a state which puts them both in superposition usually, so that we can read either one with equal probability. So those are the preliminaries. So let's get into the problem encoding part. So this is the application we're interested in doing. We have a combinatorial function. We're trying to minimize it. So it can be potentially higher order. You don't need to stop at second order, but you have a coefficient on each of the terms. And then each variable can only take the value -1 or 1. The encoding we're going to use is we're just replace every spin variable with a poly-z operator. That's 1 or -1. Now we have, there's our Kronecker product, which puts it at the ith position. And then we just build this huge matrix where we replace every spin variable with this, special sigma hat matrix, right? Now, the first leap that I'll show you in a specific example, but just believe me that for now, that the minimum eigenvector of this matrix E hat is the optimal solution or the lowest energy solution of that original optimization problem. So that's the first big leap. And that seems too good to be true because calculating the minimum eigenvector of a matrix is not an NP-hard problem, but this combinatorial optimization problem is an NP-hard problem. But the catch is that these matrices are 2 to the n by 2 to the n matrices. So we basically changed the problem from an NPR problem to a much bigger space where we just now have a much simpler problem to compute on that huge matrix. So that's the encoding part. Now let's go through an example. In abstract, maybe that's a little bit hard to follow. Here's a super easy optimization problem. We just have 2 variables, spin sigma 1, sigma 2, then be -1 or 1. We have 1 linear term and 1 quadratic term. If I just brute force every solution, right? There's 4 solutions. And the one where you have both spins as 1, which we can use the up arrow to mean 1 and the down arrow to mean -1. That's the physics notation. This is the optimal solution. So we're looking for an algorithm that would figure out, okay, if I set both the variables to 1, I get the minimum energy. From a quantum computing perspective, space is cheap. So what we're going to say is that we have our quantum vector of size n, and we're going to assign one solution to each element in this vector. And then we're going to say the probability of, well, the probability of seeing that solution is just what is the magnitude of the value in that entry. There were other ways you could think about encoding the optimization problem into the quantum computer, but let me ask you this question. Why is assigning one entry in this vector to each optimal solution a good idea? Are you answering the question? You have a different question. Different question. F of sigma, so the question is, what is F of sigma? Good point, it's not defined here. F is the minimization function, minus 0.2 sigma 1, minus sigma 1, minus sigma 2. Yeah. Repeat my question? Yeah, so why is it a good idea to make your quantum state vector, one entry in your quantum state vector equal to one of the optimal solution, or one of the configurations of this optimization problem? So he said you can measure it. So this is a very important point. If you put 100% of the probability of reading the state vector on one of these things, you do one read and you just get the optimal solution. We don't need to do quantum tomography. We don't need to look at other bases. You just get the solution you want. So one of the major challenges in doing any quantum algorithm is that you need to figure out how you're going to read the data out of the quantum computer. And this solves that problem for you. Okay, so that's what the state encoding is going to be. Here's the, if we then take the function f, or the optimization problem, we turn it into this big matrix E. Now we've got the sigma hats, right, and the E hat. This is what the matrix looks like. It's incredibly boring, right? We just have the evaluation of the energy function on the diagonal of the matrix. And if you then look at what is the eigen decomposition of this matrix, it's also super boring, where you just like have each of the entries with an eigenvector of exactly 1. So if you know what the eigenvalues are, you can then basically look at the associated eigenvectors, and they correspond exactly 1-to-1 with the state vectors you have in mind. And from this, you could just say, okay, well, that's the lowest eigenvalue. This 1 occurs in that particular state entry. So therefore, that's the optimal solution of the problem. And then we're done, right? So, I mean, this is really silly. Like the encoding is trivial if you can actually read the matrix. But the problem is we can never explicitly represent E hat. That's what we're going to use the quantum computer for. And the challenge is, like, how do you find this minimum eigenvector? What quantity corresponds to the eigenvalue? So I think you're asking the question that comes next. How do you find the smallest eigenvalue of E hat? Correct. Yeah. So I mean, that's what we need to answer. How do we find the eigenvector that corresponds to the minimum eigenvalue of the matrix E hat? That's what comes next. Is the encoding part clear? Cool. Okay. So quantum annealing, that's the setup of the problem. How do we do the solving? How do we find this minimum eigenvector of an exponentially large matrix? So we're going to do this in an analog way. And the goal is to leverage the properties of a dynamical system to find this minimum eigenvector. We're going to design an ODE where the solution is the answer to the computational task we want. So someone asked about algorithms earlier. Like, this is what an analog algorithm is. Design an ODE to do what you want. And we're going to do it with the time-varying Schrödinger equation because we're in quantum computer class. So this is the target. Let me begin by giving you an intuition with a really trivial example we all could do when we were in high school. So imagine that you have two magnets. We have the linear magnet is going to be pinned to the table. That's what the black dot means. And then we are going to control the U-shaped magnet, right? So my claim to you is that the state of the rectangular magnet tries to always align itself with the U-shaped magnet. as we change the U-shaped magnet. So watch the animation. We all know if we moved the U-shaped magnet, that is what would happen, right? Like the bar would just rotate to be in exact alignment with the U. Said another way, there is a low energy configuration of these two magnets, the ground state, if you will, that they try to stay in as you change this dynamical system. Yeah. So now here's how you connect it to quantum annealing. So the bar-shaped magnet is going to be our state vector psi. And then our U-shaped magnet is going to be a very slowly changing matrix operator, which is going to track the minimum eigenvalue of the matrix. And so in particular, it's going to stay in the lowest eigenvalue while you do this interpolation between the two states. So maybe the quantum part is not clear. Does the classical magnet part make sense? Okay. So here's the setup for the problem. We're going to have two quantum Hamiltonians, E0 and ET, so E star and E target. And then I'm going to do a linear interpolation between them. Earlier in the talk, you saw these programmable functions, AS, BS. In this part, I'm just going to say these are linear functions, the simplest version possible. You can see them right there. Yeah, so one's going to ramp up, one's going to ramp down. It's going to be super easy. So the annealing part of quantum annealing is essentially this dynamical interpolation. So we're going to start in E0, in the ground state of E0, and then we're going to slowly interpolate to E target. And the adiabatic theorem, which is essentially what I was leveraging with the magnet example before, it says that if you go slow enough, at the end of the time evolution, you will stay in the ground state of, you will be in the ground state of the target problem because you started in the ground state of E0 and you did it very slowly. Let's look at the math in a little bit more detail. So one of the most popular ways to start this is that you have the Kronecker product of the X poly. And part of the reason for that is that there is the uniform superposition state, the plus state, is the ground state of this matrix. So it seemed like apparently hardware vendors can build the uniform superposition state, so they do. And then that means they can apply this matrix and they'll be in the ground state of that initial system. And that's how you define them right there, right? And then I told you already, for our simple two-spin optimization problem, the target matrix we're looking for is this simple diagonal matrix, right? So essentially, then mathematically, what you're going to do is you start with psi 0, uniform superposition state, E0, the X product matrix, and then we do this slow linear interpolation to ET being this diagonal matrix with all of the energy values on the diagonal, right? And the adiabatic theorem says if we do this slowly enough, we will find the minimum eigenvector of the target matrix. So here's this example done numerically. So here we have S, that's the interpolation function. I'm showing you the eigenvalues of this hybrid matrix EA. And you can see that the minimum eigenvalue takes some trajectory, right? It goes up and then it comes down. And if we look at the state vector psi 0, and then I'm going to project it onto the Z basis. So we just look at the probabilities of being in a particular one of these states. You can see on the right part, or I guess it's the left, right? We start in the uniform superposition state. So we have equal probability of seeing all the different states on the Z basis. But as we do this time evolution slowly enough, the probability of seeing up, which is the ground state of the final Hamiltonian, it increases and increases and increases until we have 100% probability of seeing up. That's because we're tracking the optimal eigenvector of the this weird hybrid matrix. Yeah, so this is the evolution of the optimal state. You can see it goes to 1. And this little gap between the lowest eigenvalue and the next highest eigenvalue is actually always non-zero. So if you go slow enough, you're guaranteed to remain in it. Question? Well, so The analog quantum computers can get you in the uniform superposition state. They don't have a Hadamard. Yeah. Yeah, no, but this is the thing that's, fun and weird about using an analog quantum computer. The vendor comes to you and says, I can do A, B, C, D. It's just a fixed set of things it can do. And then you have to figure out like, okay, what cool computation can I do with like a very restrictive set of things, which usually operate on all the qubits simultaneously. So you can't think of like, what happens if, like, what if I could apply one gate to this? Some people have proposed hybrid systems where you can do gates and then switch to analog and then go back to gates. That would be really cool one day if we have it. The question is, how do you start in the uniform superposition? I have no idea. So like the vendor made this happen somehow. It's really experimental physicist question. There's another question back here. So the question is, what happens if the system has degenerate ground states? That is a great question, and it actually has a super deep answer. I'll try to give you the short version without any proof. For some Hamiltonians, ET, this will prepare a superposition of all the ground states. For other Hamiltonians, it will produce a superposition of some of the ground states, maybe with different probabilities. So it's weird. But that is what happens when you have degenerate ground states. Some ground states can even be suppressed to 0 probability. So I said earlier, you shouldn't be able to do Gibbs sampling with this algorithm, because that's why. But we actually have experimental evidence to suggest with thermalization, with noise, you can. I thought,
Carleton, before you take more questions, you have just under 10 minutes left. So if there's anything you want to wrap up with, and obviously continue to take questions for this next bit. But
yeah, so my plan is to get to the end of this math, and then I'm wrapping. Other questions? One over here. Mm-hmm. So the question is, what is the computational complexity of quantum annealing? And with some remarks that it doesn't look very good. You are correct that we're solving this Ising model problem solves NP-hard problems. So it needs to have exponential scaling, right? In the worst case. So from that standpoint, maybe you shouldn't do quantum annealing. But because we're solving optimization algorithms, we couldn't hope for anything better than that scaling, right? And a lesson that I know from doing classical optimization algorithms is that empirical performance on specific instances is more important than the scaling, right? The theory doesn't help guide us. It just says it's bad. But in practice, it can actually be quite good. And that I mentioned to you a paper with the first wall clock advantage of a quantum computer for optimization. It's using this algorithm. So for whatever flaws it has, it does seem to be working pretty well, empirically. There's one more over there. Yeah. So the question is, how big is the gap and can you have crossings? So my understanding is that the math for this algorithm in a perfect setting guarantees a gap. So you should not have one. Now that doesn't mean if you go too fast, you'll jump to a higher energy level. Or if there's noise, it could push you to a higher energy. So I think that's what's being talked about when people talk about the crossing. In terms of how big is the gap, this is how a proof that quantum annealing takes exponential time works. You study how that gap closes, and that implies how slowly you have to do the annealing algorithm to maintain yourself in the bottom eigenvector. And you can cook up a problem where that gap shrinks exponentially fast, which means that the time needs to grow exponentially long. And that's how you get like this can solve NP-hard problem type of things. There's a very cool algorithm by Rolando Soma on the glued trees problem, where they actually do non-adiabatic evolution and observe an exponential speed up from quantum annealing. So there's more sophisticated things you could do, but that's what the adiabatic theorem says. Let me move on so that I can wrap up on time. So this is an example, a numerical example worked. In this picture, what I'm showing you is how does the final state probability of this algorithm look like as you change this annealing time parameter. So in the beginning, you see a uniform superposition of all the states, 0.25. As you increase the annealing time, you see more and more of the optimal solution until you get to the adiabatic limit. I think that's, yeah, which is out here. So in this particular example, when you get to a JT of about 100, you are seeing the adiabatic limit of this evolution, and you'll get the ground state with a 1% probability. In the left hand, when you do non-adiabatic evolution, you do see some of the other states, but they're kind of prioritized by energy, which is a useful property. So that's how this example varies with annealing time. These types of analog computations are really fascinating. And if you look at the non-adiabatic regimes, the out of equilibrium regimes, you see all sorts of bizarre oscillations. So we built this software. It can go to about, so let's say 12 or 14 qubits on a laptop. And you can actually look at for kind of arbitrary analog control functions and different weird Hamiltonians, like what happens to the state evolution over time. And you can get some really crazy pictures like this one I'm showing you here, where there are 17 ground states that are kind of all oscillating, competing for who will have the probability mass. So we built these software packages. If you think this is interesting, I would check it out and play with them. So there is a fundamental challenge for quantum annealing. It's kind of going to this question about the theory. All of the interesting Ising optimization problems I know occur around 100 to 1,000 spin variables in the classical Ising space. But we can only simulate this quantum annealing algorithm for, say, 40 spin variables with hero runs on large HPC systems, which isn't big enough to access the interesting problems. So the only way to study this algorithm is to have a real quantum computer and then check, like on real problem instances, is it producing something useful? Fortunately, people built such quantum computers, so we can study it. But otherwise, we would kind of be out of luck. But it is important to remember that quantum annealing is not going to magically solve NP-hard problems. That does not match our understanding of the complexity classes of quantum computers, which is shown here. And so actually, our best hope for quantum annealing, and actually all quantum optimization algorithms, is that they could be good heuristics for NP-hard problems. So they don't guarantee ground states, they don't guarantee high quality, but maybe they are good in practice. And consequently, measuring the performance on real hardware is a really important point. So that brings us to quantum annealing in practice. I'm going to give you the really fast version of these results. Let's just focus on this benchmark. So this is the paper I mentioned before with our optimization benchmarking result. We take the D-Wave hardware. It has a particular hardware graph. We build spin glass instances that exactly match the hardware graph according to this probability distribution you see here. And then we benchmark it against a ton of classical algorithms. So on the x-axis, you have runtime. On the y, you have solution quality. And this is relative from the best known solution. The black line here is the solution quality that comes out of D-Wave's hardware. And you can see it's lower to the left. So for a fixed amount of time, for a very short amount of time, it's the best solution that you can get. And then you have all the classical algorithms up to the right. And two of them, parallel tempering and simulated annealing, with enough time, like on the order of 100 seconds or 1,000 seconds, will find equal quality solutions or even better solutions than the analog quantum computer does. But for very short timescales, like 10 seconds or 1 second, you actually get higher quality solutions from this device. So again, we know worst case scaling will be bad, but here's an example of real measurements that are pretty good and pretty interesting. So that is that. Let me say, I just want to mention, what is the future of analog quantum computing? And this is kind of my pitch to you guys. I think the case for condensed matter theory research is now very solid. Since 2018, we've had, a great line of papers of how to do this. So what's the next big grand challenge? That is actually to try to use this technology to improve finding real materials. This is a collaboration I have with Vivian and others, where we're using quantum annealing to try to accelerate the material discovery process. We're working on that right now. We're pretty excited about it, so that's going to be fun. But just to wrap up, I think analog quantum computing is awesome. I hope I might have started to convince you today as well. I think it's already shown a lot of utility for condensed matter physics. And we're starting to see potential applications in optimization and material discovery. The primary challenge is how do you get this close match between the application you want to solve and the hardware's native Hamiltonian. But I'm sure you guys are really smart. And now that you've seen what is possible, you can come up with a lot of good ideas. So please go for it, write awesome papers, and thank you for your time.
If there are just one or two more questions, we could take them now, and then we'll just move into the break, and you're welcome to continue talking to Carleton. Go ahead in the front.
Yes, my question is I think analog quantum computing is definitely really interesting, and I was wondering I think unlike say circuit level quantum computer, so where can we get access to this analog quantum computing?
So the question is, where can you get access to analog quantum computing? That is a great question. So both D-Wave and QEra provide cloud-based access. So the D-Wave one is very easy. You can get a few minutes for free just by making an account. It's called LEAP is the keyword. QEra, I think you have to contact them by email and request access. I don't know if they provide free access now, but I'm sure they would love to hear from you. So you should reach out to them and say, tell me about how to get access to your device. I'm interested in playing with it.
We had a question in the back.
Looks like better, but how about the other material which is like Hamiltonian is not different by quantum computer? What do you think is better for it?
So the question is, when the quantum computer is a good fit for your Hamiltonian, that seems like a good idea. But what do you do when it's not, right? And I think that is one of the best arguments for gate-based quantum computing and fault-tolerant quantum computing, right? It can support, at least in theory, every Hamiltonian. So it will be able to do everything you want. The story becomes more nuanced when you look at the resources. Like, how many gates is it going to take to implement a fermionic Hamiltonian in a fault-tolerant system? It's not that trivial. You have to encode the problem, and then you've got a lot of complicated operations to do. But I think that's our best hope for the most complex Hamiltonians and when we need the highest accuracy requirements.
All right. Feel free to continue bringing questions to Carleton during the break, but let's thank Carleton again.